Hello. Now we are going to learn about Integrated Modular Avionics, IMA. I'm your Logeshwari. Let's go. Introduction to IMA. IMA is an advanced avionics architecture that integrates multiple systems into shared computing resources. Definition of IMA. Integrated Modular Avionics refers to the use of standardized modules that perform specific functions, promoting efficient system integration within aircraft. Benefits of IMA. IMA promotes reduced weight, improved reliability, streamlined maintenance, and adaptability to changing mission requirements, making it a crucial part of modern aviation. Why IMA is needed. Reduces aircraft weight, wiring, and overall hardware. Increases reliability using modular and redundant systems. Allows easy software upgrades without replacing hardware. Improves data communication and real-time performance. Enhances maintainability and lowers lifecycle cost. Traditional avionics versus IMA. Its table represents here its key feature like architecture, hardware, weight, wiring, upgrades, efficiency, data sharing, maintenance. IMA Architecture Overview. Integrated Modular Avionics, IMA, architecture replaces multiple standalone avionics units with a shared, modular, software partition system. The architecture includes 1. Core Processing Modules, CPMs. 2. Partitioned Operating System, ARINC 653. Core Processing Modules. High-performance shared computing units in IMA. Host multiple avionics applications simultaneously. Provide redundancy for safety-critical operations. Modular design allows easy replacement or scaling. Support deterministic timing for real-time tasks. Partitioning in IMA. Separates avionics functions using time and space isolation. Prevents one task from affecting others in failure conditions. Ensures predictable and safe execution of applications. Supports multiple safety-critical levels on same hardware. Defined by ARINC 653 standard. ARINC 653 standard. Defines partitioning rules for avionics software. Uses time division scheduling for predictable execution. Ensures memory protection between partitions. Supports mixed criticality applications safely. Standard used in Airbus, Boeing, and military aircraft. Communication Bus, ARINC 664. Ethernet-based aircraft data network for high-speed communication. Provides deterministic, guaranteed bandwidth data flow. Ensures reliable point-to-point virtual links. Reduces wiring complexity compared to traditional buses. Used for connecting processors, sensors, and cockpit displays. High-level data flow. Sensors send data to I/O modules for digitization. Processing modules compute navigation, control, and monitoring tasks. Data moves through AFDX network to cockpit displays. Applications run inside isolated partitions. Commands are sent back to actuators for flight control. IMA block diagram. Shared processing modules connected through a ARINC 664 network. Partitioned OS running multiple avionics functions. I/O modules linking sensors and actuators. Redundant power units ensure fail-safe operation. Displays and controllers integrated into the same network. Resource sharing in IMA. CPU time divided among partitions using fixed schedules. Memory is allocated with strict isolation for safety. Network bandwidth shared using virtual links. Efficient hardware use reduces system weight and cost. Ensures real-time performance without interference. IMA hardware modules. Core processing modules, CPMs, for computation. I/O interface units for sensor/actuator communication. Network switches for ARINC 664 connectivity. Power supply and backup units for safety. Rugged enclosures for vibration and temperature protection. Software layers in IMA. Application layer for avionics functions, navigation, control. Middleware for communication and data handling. OS layer implementing ARINC 653 partitioning. Hardware abstraction layer providing unified access. Device drivers managing sensors, I/O, and communication. Fault tolerance and redundancy. Multiple processors provide backup during failures. Real-time fault detection and isolation mechanisms. Redundant power and communication channels. Ensures continuous operation in critical systems. Increases aircraft safety and reliability. Benefits of IMA. Reduced weight, wiring, and hardware boxes. Improved reliability and system safety. Easy maintenance and software-based upgrades. Higher computing efficiency through resource sharing. Better data flow between avionics systems. Applications in modern aircraft. Airbus A380, A350 and Boeing 787 use full IMA. Fly-by-wire flight control systems. Engine control, monitoring, and health diagnostics. Navigation, communication, and display systems. Military drones and advanced fighter jets. Challenges in IMA. High certification cost, DO 178C, DO 254. Complex partition scheduling and system integration. Cybersecurity risks due to shared networks. Requires highly skilled engineering teams. Long development time for mission-critical systems. Future trends. Use of AI and machine learning for avionics optimization. More powerful multi-core and heterogeneous processors. Cloud-connected predictive maintenance systems. Increased automation and autonomous flight systems. Lighter, more integrated avionics modules. Conclusion. IMA replaces heavy federated systems with modular architecture. Offers higher reliability, efficiency, and maintainability. Supports modern aircraft with advanced digital functions. Expected to dominate future avionics platforms. Essential for safety-critical, high-performance aviation systems. Thank you.